Hey, this is Horner, and this is section 5.1. This is the free response question for torque and rotational statics. This is the first question, and they have a uniform disc, and it is mounted to an axle. So the axle is right here, and it's allowed to rotate, and there's no friction, which makes this a lot easier. There's a thin uniform rod, so this is the rod, and it is attached to the disc so that it will rotate with the disc. So you can see kind of how it's bolded here. There's also a block that's attached at the end, and then they give you the properties of the disc, the rod, and the block. So notice that this is going to be a rotating system. The system is held in equilibrium with the string, so we know that all of the torques should be equal to 0 when you sum them up. And they want us to go through, and they want us to find out what the tension in the string is. So they want to know, basically what is T for this string. So we're just going to go in and we want to know what is the tension, so capital T, in the string. Before we do that, we also want to kind of take a look here at the triangles that are made. So one of the triangles that you'll see is the one that goes over here and then kind of comes back down. So there's your angle. So for this rod, we have both the rod times the sine of the angle will be this distance, and then rod times the cosine of the angle is going to be here. Same type of thing is going to happen for the block, so we'll just have to remember that as we go through. So to find the tension in the string, best thing to do is start off with the sum of the torques. So we know that the sum of the torques for this system should be equal to 0. That means that the torque generated by the rod, and notice that the torque on the rod is this way. So that would be counterclockwise, and we said that counterclockwise from our perspective will be positive, plus we have the torque of that block that we know is up top because it's going to rotate the same way. So that is the torque of the block, and from that we are going to subtract off the torque of that string, and that should be equal to 0. So let's go ahead and put everything in that we know about these. We know that for the rod, mass of the rod is m, and then we've got gravity, and so you have to remember torque, let's go back here for just a second, is F times R. And so we're going to do m times g times r, and then we're going to do times the sine of that angle, because we do have the angle here, and we know that the string is attached right at this point. So the rod is a distance, an angular distance theta, and so this is really going to be torque is equal to FR sine of the angle. So now we've got mgr sine of the angle plus, now for the block we see has a mass of 2m. So this is going to be 2mg, and then it is at twice the radius. So radius of the rod, that block is at twice the radius, and then we have to do sine of the angle again. And then we subtract from that the tension, which is the force, times r, and because this is at a 90-degree angle to the line of action, so these two are at a 90-degree angle, we don't need to put in sine of the angle, so this is equal to 0. From here it's just math. So the physics part is this first part, and then the rest is just going to be algebraic manipulation. So let's go through and do that. We've got TR is equal to mgr sine of the angle plus, now we go ahead and multiply this through, and we get 4mgr sine of the angle. So we want to solve for t, so we're going to divide both sides by r, and we can go ahead and sum these two things. So we've got 5mgr sine of the angle, so let's make this look more like an r, and we're going to divide by r, so our r's cross off, and the tension in that string now is equal to 5 times mg sine of the angle, which is really interesting because we're not worried about the radius now anymore. The radius is gone, and we're just worried about 5 times the weight, okay, times the sine of the angle, and that is the tension. If you cut the string, then this thing should rotate, and when it rotates, notice that it's going to rotate counterclockwise, which is positive, so that's a good thing. We need to find the angular acceleration, and then to do that, we know that torque is equal to the moment of inertia of the system times the angular acceleration. So this is really the sum of the torques, should be equal to that. Let's go ahead, and we know the sum of the torques already. We did that. We've got to go through and find the total moment of inertia. So this is I total for our system. So that would be the moment of inertia for the disk plus the moment of inertia for the rod plus the moment of inertia for the block. And if you go back up, they do give you the moment of inertia equation for the disk and for the rod, but notice they don't give it to you for the block. Just remember that that is kind of like a point mass, and for point masses, the moment of inertia is going to be equal to just mr squared. So that's one that you really need to just kind of recognize when you go into this. So our I total here is going to be equal to what they gave us for the disk, which is 3/2 mr squared, plus the rod, which is 4/3 mr squared, plus, now you have to be careful because remember, this is the mass of the block times the radius of the block from the center. And that's not just mr, that's going to be 2m, because the mass is 2m of the rod, times 2r, because it's at a distance twice the radius of the rod itself, and that's squared. We now need to go through and put in a common denominator, and that common denominator is going to be 6. So this is going to end up being 9/6 mr squared plus 8/6 mr squared, plus this would be 2 times 4, which would be 6, and then we have to multiply that out so that we get up 2 times 2 is 4 times 2 is 8, sorry. So that'd be 8 times 6 is 48/6 mr squared. Now we can find the I value, and so now we have, if you add everything up, that should be 65/6, and you can't reduce that anymore, mr squared. So now we've got that part. Next thing we need to do is we need to find alpha. So alpha is equal to the sum of the torques, all divided by the moment of inertia. We know from the previous part that our tension in that line was 5 mg sine of the angle. So if I want to know what the torque is, I just have to multiply that times r. So I end up with 5 mgr sine of the angle. And we're going to divide that by our moment that we just found, which is 65/6 mr squared. Now that we've got that, we need to go through and do some reducing, so we can get rid of 1r there. We can get rid of the masses. Then we can move the 6 up to the top, and then go ahead and do our masses. 6 times 5 is 30, so we're going to have a way that we can go through and reduce. And when you do that, you should end up with 6 times g times the sine of the angle, all divided by 13 times r. And that would be your final equation for the acceleration of the system. They want us now to find the linear acceleration of the mass about the end. So we know that linear acceleration is just equal to angular acceleration times r. And so what we'll do is we're going to take this expression and multiply it times r. And if you do that, you'll notice that well, you're going to have to multiply it also by 2. So we have to multiply by 2r because we want the end of the rod. And so the end of the rod is going to be 2r. So this is going to be equal to 6g sine of the angle over 13r times 2r. r's cross off, and we're going to end up with 12g sine of the angle all over 13. And that would be our linear acceleration. For the very last part of this problem, as the disk rotates, the rod passes the horizontal position shown above. Determine the linear speed of the mass at the end. So we want to know what is the linear speed of this, and we're going to just say that that is our direction. So what is it that this thing has at this point that is going to be given up as it rotates down? And we know that we can just use energy here. So we know that the change in the potential energy is going to be equal to the mass times gravity times the height of that rod plus mass times gravity times the height of the block. And so you have to remember here, when we measure height, we want to do it from the center of mass of the rod and from the center of mass of the block. So in order to get that done, we're going to say this is delta U is equal to, now we're going to do mg, and then we've got the radius, okay, for the rod. So the radius of the rod's going to be here, and it's going to fall. But remember, it kind of falls in an arc like this. So this is going to be mgr times the cosine of the angle. So of that angle that we had. And then this is plus, now remember this is double the mass of the rod, so that's 2mg. And then the height of the block is going to be double the radius, so this is going to be 2r times cosine of the angle. All right, so now we know what the potential energy change is. We know kinetic energy is just equal to I omega squared. And remember what we're trying to find here is the linear speed. So we're going to go ahead and use this since it's rotating, and then we can go back and find the linear speed later. So now we're going to say that K is equal to, the change in kinetic energy should be equal to change in the potential energy. So this is going to be I omega squared is equal to mgr cosine of the angle plus 2mg2r times the cosine of the angle. And at this point, let's go ahead and plug some things in. So this is going to be 1/2. Oops, sorry, I forgot the half here. 1/2 of, here's our 65 over 6 mr squared from earlier times omega squared. And then that's equal to mgr cosine of the angle plus 4 mgr cosine of the angle. So if we go through and solve for omega, omega will be equal to the square root of 12 times g times the cosine of that original angle, all divided by 13 times r. So now what they want us to do is use the relationship between the two to find out what that linear speed is. So we know that linear speed, so that looks like a U, let's make it a V. Linear speed is equal to omega times r. And so here we're going to say linear speed is equal to the square root of 12g cosine of the angle over 13r times 2r. And with the magic of math, we can go through and we can actually factor out. So we've got 12 here. And so that's going to be 4 times 3. So this is equal to 4r. Okay, so we've got, oops, sorry, not 4r. This is equal to, I'm going to back this up for just a second. That is, we've got 12 cosine of the angle, so let's go ahead and back this up to, there we go. All right, so this is going to be 4 times 3, so this is the square root of 4 times 3, okay, times g times the cosine of the angle all over 13r. And that is multiplied by 2r. So if I go ahead and I factor out, if I not factor out, but if I take the square root of 4, that ends up being 2. So now this is equal to 2 times this 2. And then the other thing I'm going to do is I'm going to put I'm going to take and multiply the top and the bottom both by r. So if I multiply the top and the bottom both by r, I get, r squared on the bottom here. And if I take that and find out what it is, I end up with 2 times 2 times the square root of 3 times g. And then I'm going to go ahead, 3 times g times cosine of the angle times r, and that's under the radical, all over 13. And then we have an r on the outside because this r will go there. So we've got this r, and then we have 1 over r. That 1 over r came from the r squared that was on the bottom. And now I can cross off these, and the simplest way to have this is the square root of 3g cosine of the angle times r all over 13. Now, could we have just left it like this? Absolutely. And they should give you full credit for that. I wouldn't see why they wouldn't. But if you wanted to go through and do the rest of this math and make it even simpler, you sure could. And that is the end of this problem.